The plan for your last talk of the day is to discuss how computers can make decisions. And when I say making decisions, I mean making decisions about things that are in the real world, or at least maybe on the internet, which is like next best thing. So images, sounds, tweets, Facebook posts. How can we have computers make decisions about these objects that are usually consumed by humans? Like it should be, I mean, people look at pictures and people listen to sounds and they make decisions about them. So how can we accomplish kind of a similar thing with a computer rather than a human? So I'm going to start from the basics, and we will work our way up to a program that allows a computer to make a decision about images. And in particular, it's going to be able to distinguish between images that have different colors in them. But before we get to that, way before we get to that, what you need to know is that everything a computer knows and everything that a computer makes a decision about is a number. That's all your computer gets is numbers. So when you listen to something from the iTunes store, or you're browsing the web, or you're consuming any kind of media on a computer, internally that medium is represented by numbers. So if you have a picture of Grumpy Cat, then Grumpy is represented by a bunch of numbers. So from your computer's perspective, Grumpy Cat is a big long list of numbers. That is it. So if you want to make a decision about the image that is a picture of Grumpy Cat, then you need to be able to reason about the numbers. And so like, we often have computer science students come here and say, oh, I love computer science, but the math, I don't really care so much about the math. Let me tell you, you really can't have one without the other, okay? So we are going to talk about numbers and math for a little while, all with the goal of developing something that computers can make use of. So every decision a computer makes is a decision about numbers. So we're going to have a bunch of numbers today. Okay, so crash course in image processing. This is only going to take a little while. The first thing you need to know is that images in a computer are made up of pixels. So each little tiny dot that makes up this picture of Grumpy Cat is called a pixel. You probably heard the word. And each one of these, its color value is represented by 3 numbers. There's a number for how red the pixel is, a number for how green the pixel is, and a number for how blue the pixel is. If any of you guys have already done maybe some web programming or done some HTML or stuff like that, when you specify colors in HTML, you say, I want this much red and this much blue and this much green, for example. Okay, so pixels of Grumpy Cat are the same. So numbers, right? They're just numbers. So the pixel with all zeros, 0, 0, 0 for red, green, and blue is black. 255, 255, 255 is white. I'm not going to talk about why it's 255. That might seem like it just sort of came out of nowhere, but never mind that for now. Somebody else will give that talk later. So all we need to remember is a single pixel of the image is represented by 3 numbers. So a more illustrative version of what Grumpy Cat looks like to a computer is groups of 3 numbers in a big long list. Each one of the groups represents 1 pixel. Each pixel's got a red value and a green value and a blue value. So like this pixel here, wherever it is, has got a bunch of red, not so much green, and a little bit of blue. Maybe it's like the dude's hand over here who is holding him, right? Because it's a little more sort of pinkish colored, could be. Another pixel elsewhere that has maybe a little bit more blue might not be, maybe it's you can see his iris is a little bit blue, for example. Anyway, so each one of the dots has a corresponding set of 3 numbers that describes it. Now, given the size of the group of people that we have, it is reasonably probable that there's at least one person who's colorblind. And you might think, this is going to be really boring. But it's not going to be so bad, because I am always going to provide you, when we're talking about colors, the 3 values. And all the reasoning that you're going to do about the 3 values and like all the little exercises that you're going to do are going to use the numbers. They're always going to be in order, red, green, blue. So whether you can see the difference between red and green or not is not a disadvantage for this talk. You can just read the numbers. Just as for a computer, I mean, all it's going to do is read the numbers. So given that everything really is just numbers, anything that a computer is going to do is accomplished basically by arithmetic like adding, subtracting, multiplying, and dividing, and a few other things, but basically that. Or asking a question about the numbers that are representing the things that it's dealing with. So asking a question like, is a number greater than another? Is it less than another? Are they equal? And then besides asking those sort of really simple questions about just two numbers, we can string the questions together with the words and, or, and not. So I can ask if x is greater than y and a is greater than b, and I can get the answer to that whole thing all together. So this is it. This is all the computer is doing on the inside. That's all you get. So what we're going to do is talk about how can we express decisions and operations on images as decisions and operations about numbers. So, I'm going to show you all through like little snippets of code. They're going to be in Python, which doesn't really matter, except that it's a nice, easy, elegant language. And I just want to show you that even though I'm showing you some code, even if you haven't seen Python before, it doesn't matter. It's easy to understand. This little piece of code says x is 10, y is 2, z is x divided by y. And this means what you think it would mean. And then we can print out the values that we've told the computer about. Z, of course, is going to be computed by the computer. It's going to do the division and get the answer. So it can print stuff like 10 divided by 2 is 5, which I grant is super boring. But we're going to operate on more interesting things, and we're going to ask more interesting questions. But the important thing to remember is down at the core, this is the only kind of stuff that we're really doing. So rather than just operate on numbers, like little dorky numbers that we just put into the code, let's see what we can do if we know that images are represented by pixels and the pixels are represented by numbers. So I can take Grumpy Cat's pixels. There they are. And there's nothing stopping me, if I have my computer, from doing some arithmetic on these pixels and seeing what happens. So for example, I can divide Grumpy Cat by 2. And by dividing him by 2, what I mean is I'm going to take every pixel value and I'm going to divide it by 2. And then the result is going to be a new image that has smaller values. Oh, that's wrong. 60, right? Should have been 60. But, and these are all right. The result of this is a new image with new pixels. And because all their values are smaller, everything is closer to black, which means that we get an image that's darker than the one that we started with, for example. Okay? So to a computer, the idea that you can divide an image by 2 is totally natural. It's like, well, I'll just divide all the pixels by 2. Since in the computer everything is represented as numbers, this is totally legit and not weird in the slightest. Okay? So this was image processing 0. We can also make decisions about numbers. Here again is a very sort of boring example where I'd give the computer two numbers, x and y, and I can ask, is x greater than y? And in particular, I can say to the computer, well, if x is greater than y, I want you to print this thing here, x is bigger than y. Otherwise, if that's not true, I want you to print this other thing. And again, if you've done any programming at all, this will be totally natural. Even if you haven't, it's, if you just imagine the most likely thing that this means, you will be right. Okay? So we can make decisions about numbers. And again, because we can make decisions about numbers, we can make decisions about images. Let's talk about making decisions about individual pixels first, and then we'll talk about how do we make decisions about like the entire image all at once. All right? So one question I might want to ask is, does the pixel have more red or more blue in it? Okay. So I can use exactly the same kind of code that I showed you before, except it'll be a little bit different. So on the left, image xy just represents the pixel at some spot in the image. Its red value, so the red one, is this bigger than the pixel value at the same spot, x and y, maybe here, and its blue value? All right? So we can write an if statement. We can ask the same kind of question. Is the red piece bigger than the blue piece for this pixel? And it's true for this this pixel here. Red's bigger, smaller for this one, and it's smaller for that one. So what I can do, instead of printing something out, for example, I can identify the pixels where there's more red, and I can produce a new image where the pixels where there's more red are painted in totally solid in red, and the pixels for where that's not true, I'll paint them in blue. And this is another kind of image processing. If you want to pick out different regions of the image where different colors are important, you can just do this by asking a question about the pixels, and that question is a question about numbers. So in my processed image here, you can see that so that little bit of blue right there and this right here correspond to Grumpy's iris right there and here, which is a little bit more blue. This little patch of blue is the dude's blue jeans here. And then this little patch here is blue jeans here. So you can see that most of the image actually has more red than blue in it. The image overall has kind of an orangey color. It's pretty slight, but it's there. But there are a few regions where the blue is more important. Okay? Again, all this to say, we can look at individual pixels, know that they are numbers, and then make decisions about them. So I mentioned that I don't want to just talk about individual pixels. I want to talk about the entire image as a whole. So what we're going to do is, for any image that our computer sees, we're going to compute a summary of that image. That's not all the values of all the pixels, which gets a little bit hairy to work with. We're going to work with something that's a lot more simpler, but still preserves the information that we need. So what I'm going to start by doing is looking at the average pixel. So the average pixel has 3 values, and each of these values is the average value of red over the entire image, the average value of green over the entire image, and the average value of blue over the entire image. So the average, in this case, what I mean is the mean, to be a little bit more specific, and you could think of it as just kind of like the value of red that's sort of in the middle among all the values of red that are in the image. Okay? So all of the pixels go into this number, but we've lost a bunch of information. We don't know anymore that his nose is kind of pink and his eye is kind of blue. We only know that overall this is how much red is in the image. And overall this is how much green, and overall this is how much blue. But that's going to be enough. And the reason it's going to be enough is that if we have a different image that has a different color distribution, it's going to have a different average pixel. So if you take Creepy Blue Cat here, his average pixel, and this is the actual real deal, I computed this, his red average is much lower, and his blue value is much higher, which is reflected in the fact that it's mostly blue. His green value is actually pretty big as well. That's probably from, I don't know if you can really see, but there's like a window frame over here that's mostly green, and his irises are green as well. And the little bit of red is probably coming from his nose, and then maybe this little orange piece sort of up here. Okay? So the average pixel is a summary of kind of everything that's going on in the whole image in terms of what colors are present. But that's what we're going to use for our example today for classifying images. Except it's not exactly what we're going to use. I'm going to make one more little change. And the reason is that we need to think about, so I'm going to want to classify images according to color. In particular, I don't care about the relative brightness of different images. I only care about what colors are in them. So whether or not the average pixel is a good summary and is going to let us make good decisions, it depends on the decision you're going to make. And the problem that I've got with just the average pixel is that if I go back to my Grumpy Cat where I divided him by 2, their colors are the same. It's just that one's darker than the other, but their average pixel is quite different. Okay? So I want a summary that is not affected by the brightness of the image. I just want to know how much red, how much green, how much blue, but I don't really care about is it overall very bright or overall very dim. So we're going to do one last step, since we're today only going to talk about deciding about color. Now, the last step we're going to make is, instead of using the average pixel, I'm going to use what's called the normalized average pixel. Actually, I made that up, but that's what we're going to call it. So all it is the average pixel divided by its sum. So before, the average pixel of Grumpy is 155, 135, 115. But the average pixel, I just divided each one of those things by the sum of all three, and I get a number between 0 and 1 for each of them. And I can still see that there's more red than anything else, for example. And the advantage of doing this is that even if I take another image that's maybe overall darker or overall brighter, I get the same normalized average pixel, which is nice because that means that we can treat two images that have the same colors in them but are different brightnesses. We'll treat those as being exactly the same, okay? And in the example I want to show you today, that's going to be a good thing. It's not always going to be a good thing, right? Like, if what you want to do is build a thing that figures out if an image is too bright or too dim, obviously this is not the way to do it. But for what we're going to do today, it's nice because we have what we call invariance between brightness values. So we say that the normalized average pixel is invariant to changes in brightness. That just means that it stays the same if you change the brightness. Okay? So we talked about how do we represent images as numbers in a computer. And we talked about different ways of looking at that, like individual pixel level, now as a summary of the entire image. And this summary is all the information that we're going to use, is all the information we're going to use about an image in order to make a decision today. Okay? So from our computer's perspective today, an image gets translated to just these three values, and we're going to ask questions about these three values to make decisions. So I just want to mention that we can still distinguish between colors the same way that we could before, actually a little bit better. If you look at Grumpy's nap, then the red is much bigger than the blue. And if you look at Creepy Blue Cat's nap, the blue is the biggest one by far. And then we've got less red and less green. Okay, so we haven't lost any information about the colors. So this process of, okay, I want to distinguish images based on their colors. What representation do I use? How do I summarize the images is called feature construction. And in statistics and machine learning, when we're trying to build systems that can recognize different things like forest from desert or cancerous cells from non-cancerous cells or whatever else, and a really important step before we start building a system that does that is deciding what are the numbers that best represent the objects that we're trying to classify. So we're going to use these nap things. And once we have the nap values, we're going to be able to write if statements just like we saw at the beginning. So I can ask, if the green value of the nap of an image is 0.8, then that tells me that the image is really, really green. And maybe that's a useful decision to help somebody decide if they've taken a picture of forest or desert. Like, you know, you could imagine trying to map how much of a region is desert and how much is forest. This kind of question would be relevant to that. Okay? And I want to mention, too, that even though these little examples, the results of the decisions are just me printing different stuff, which is maybe not super exciting, the result of the decision doesn't have to be printing something. It could be all kinds of things. You could post to Twitter. You could turn down a thermostat. You could order pizza. Because computers are so prevalent and can control so many things, these decisions can have impacts in whatever way you might need them to have. OK, so grab a piece of paper, and I want you to think about and answer the following. So I've got a little skeleton if statement here where the question is missing. Okay? And I want you to fill in the question so that the right thing happens in terms of the print statements. So down at the bottom, I've got Grumpy Cat and his nap, and Blue Cat and his nap. And I want you to ask a question about these values. Assume that your if statement only gets one of these cats at a time and decides whether it's grumpy or blue. So in the question, you can use red, green, and blue. You can use greater than or less than. And you can use, if you need to use a number like 0.3 or something, that's fine as well. For example, here's one, oops. Here's one question, oops, sorry, that you might want to ask. Anyway, just as an example. So think that over, I'll give you a minute. You can do it on your own or do it in a group or whatever you like. Okay, what do we got? Any volunteers? Give me a question. Yeah. Red greater than 0.25. Okay, yep. So if red is greater than 0.25, then, oops, there we go. Grumpy's is 0.38, so we will know that the cat is grumpy right away, so that's true. That's good. Any other ones that are different? Yes? So this would be the simplest one, you're saying. Why is it the simplest? Yep, okay. So these both only use red and they use a constant and that's it. One of them is equality and one of them is greater than. That's good. They both work. Yes? Okay. Oh, so disappointed everyone else who said that. Yes, also fine. That'll work. Yes? Oh, some arithmetic. Okay. Red minus blue equals how much? Sorry? 0.10. All right. Any other ones? Okay, so good. Right. So you've correctly identified that there are a bunch of rules that I could use to distinguish between these two cats. Do you know if you would like one better than the other? Depends what you're trying to do, right? Like, if you're only ever going to see these two cats, then like, who cares, right? Think about this, though. Cameras are noisy things. Even if you take a picture of the same thing with the same camera twice, you often get slightly different pixel values. And that might mean that you might get slightly different values for your nap, which can mean that if you're basing your decision on equality, you are maybe not going to correctly identify Grumpy Cat if you see a slightly different picture of him, okay? Now, I mean, what you gave me is perfect, and that exactly satisfied what I asked for. I just want to start thinking about what are the consequences of choosing any one of these rules. Let's try another one. Okay, what do we got? Yes?
If nap red is not equal to nap green.
Oh, okay, red. I'll write it like this, not equal to green. Other ones? In the back, sir? If blue is 0.28. Somebody give me one with a greater than or a less than, please. Okay, right, so good. We got the hang of this, that's clear. Again, same considerations as before. If you depend on equality and you get a slightly different picture of the yellow cat, this might or might not work, but that's cool. How about this one? So what I want to do in this case is I'm telling you that the blue cat and the yellow cat are not grumpy, but Grumpy Cat is obviously grumpy, right? So what I would like is a question that distinguishes between grumpy versus not grumpy. I'll give you a minute. It's not equal to, geez. It's not equal to 0.28, okay. Someone, yes, hey. Well, if blue is higher than 28 or lower than 28, then it's one way, and if it is exactly 28, it's the other way. So you can ask it the other way around. Yeah, yeah? Okay, so you had an and in there, which was not technically allowed, but I think what you brought up is that it would be easier to solve this question if we had two questions that we were allowed to ask instead of just one, or if we were allowed to use and. Okay, so here's another. I'll give it to you. So let's write it this way though. So the first question you were going to ask was if red, what was your threshold for red? Sorry, I can't hear you. 38? Okay, so that'll be my first question. If red is bigger than 0.38, oh, there's no cats like that. Did you mean the other way around? Do red greater than green? Red greater than green. So if red's greater than green, then we're going to say that the cat is not grumpy. Is that true? No. Nope. Okay. Other way around? All right. Okay. Other way around. So if red is greater than green, on the other hand, we come down and we get asked for question 2. So red is less than green identifies which cat? The blue cat, right? So when this is answered in the affirmative, we know it's the blue cat and we know he's not grumpy. If this is false, then we have to distinguish between the grumpy cat and the yellow cat, right? So what we did by asking 2 questions was first, we picked off one of the examples that was a problem. The blue cat, we identified him as being not grumpy, and it's like, okay, we're done with that case. Now we have to separate grumpy from yellow, and we did that in the last slide. For example, I can do that by asking, is green less than 0.34, say? Okay, so sometimes one question's not enough. Sometimes, depending on the data that you actually have and the decisions that you want to make, you might want to ask more than one question. Or you might want to ask a fancier question that has like an and or an or a not in it. That's fine. So here's another example of a solution to that problem where I'm asking 2 questions. First, I'll ask about nap red. If it's less than 0.33, I'll say the cat's not grumpy. This question also identifies the blue guy, by the way, right? Otherwise, I'll take a look at the green value and I'll decide if it's grumpy cat or the yellow cat. Okay. So now we're asking more complicated questions to make more complicated decisions. And what you have just built, what we have just built together, is called a decision tree. And rather than writing it as a bunch of if statements, which gets kind of clunky, computer scientists will often instead draw a picture. And the picture has a circle for an ellipse for every place where you ask a question. So there's 2 of them because we had 2 questions. And based on the answer to this question, you go down the tree one branch or the other until you hit the bottom. So the first question is nap red less than 0.33? If that's true, we know the cat's not grumpy. If it's false, then we ask another question, and then we go left or right depending on the answer. A couple of little things about trees. So in computer science, for some reason, trees have their roots up in the air and the branches grow down towards the ground. I have no idea how that started or why we do that, but this node's called the root. It's where you start. And these things down at the bottom are called the leaves, which is backwards, but there you go. But this idea of expressing a decision as a decision tree, as a series of questions that you ask about your data, is used in all kinds of applications, especially in medicine, actually, where sometimes there are situations where you don't have access to a computer, like imagine your Doctors Without Borders kind of thing. And you need to make a decision about what is right for a particular patient. If you can express the rule that you want to use as a decision tree, then the piece of paper is good enough, right? So it's nice because it's easy to understand, and it's also nice because, as we're going to see, it's possible to learn a decision tree from data, and I'll tell you what I mean by that in a minute. So here's the thing. So any image that I can get a nap for, I can put through this tree, and I can get an answer, right? It doesn't matter. And I can put like a new unseen cat that I have not seen before through this, and I can see what it thinks. Anybody tell me what the green cat ends up as? Not grumpy. So first question is about red. Is it less than 0.33? This new dude's red is only 0.28, so that's true. So he's not grumpy. This tree says he's not grumpy. Maybe he is. I don't know this cat, right? So this tree has made a decision about any image that you could ever possibly give it. And it categorizes all possible images into grumpy or not grumpy, which might or might not make sense, but there you go. What can happen is as you're using your decision tree, sometimes you're going to get new data that don't have the answer that you would like. Like maybe this cat is actually super grumpy. And if that's the case, then we're going to need to revamp our decision tree to fix it. So now I'm going to say, oh, no, that was wrong. Let's build a different decision tree. And I'm telling you that these cats are grumpy, these cats are not grumpy, and I want to be able to distinguish between them. So I'm going to give you 3 minutes. Think about this, draw a decision tree, and then I'm going to ask for a brave volunteer to come up and show it to me. You ready? Can you use or? No, don't do it with or. Just use greater than or less than. And don't need any ands or any ors or anything. I hope that doesn't mess too many people up. But ask as many questions as you need to ask, right? The thing with the decision tree is like, ask your first question, then figure out your next question, and then, yeah. Thank you. Okay, let's see what we got. So can you help me, walk me through here? So what's the...
So that's supposed to be for nap red is equal to.
Okay, yeah, no problem. So, okay, so the first question is, if nap is red is equal to nap green, then... If that's true, which cat did we get by that?
If it equals the yellow cat.
The yellow cat, right on. Okay, so and the yellow cat is not grumpy, and so we're done. Because it doesn't get any, none of the other cats come down this side of the tree. If it's false, what's your next question?
If nap blue is greater than 0.3.
If nap blue is greater than 0.3, and so that's true for
Blue cat.
for a blue cat. Right, okay, so he's not grumpy, so we're good. And then the other cats are both less than 0.3?
Or equal to.
Or equal to. Oh yeah, or equal to, so we're good. So perfect. Thank you very much, I appreciate it. Okay, so we've got, that is right, thank you. Okay, so here's another tree that's similar. It would answer the same thing. That one was also fine. It would make the same categorization. So I think we've got the feel for how you could build one of these by hand. The thing about it is that you often don't want to just use a few examples. You want to use a lot of examples to build this thing. And the reason is that you want it to apply in the future to all kinds of different scenarios. So I don't want to put like 4 cats in. I want to put like 4 million cats in. And then, train using that data, find a decision tree that does well on those, and then it's very likely that future cats that I encounter will be correctly classified as well. So for the remainder, I'm going to imagine just classifying yellow cats from green cats, and you can see that I've taken the images and then I wrote down their nap values for each one of these images. And you can already see, now that you have some experience with this, that like the yellow cats have a lot of red in them, and the green cats don't generally, for example. And you can also see that if I look at the blue, well, there's kind of, medium amounts of blue, but there's also kind of medium amounts of blue over here. So we're going to want to think carefully about which feature, so each one of these red or green or blue I'm calling a feature, which one of these are we going to ask about first? So rather than do them by hand, there is an algorithm that is used for building decision trees. Okay? And it has 2 main steps. And the first step is to identify the feature that best separates the data. And by that I mean, if I just ask a question about that feature, how well can I divide up my cats into mostly yellow and mostly green? Okay? In this case, if I look at the red ones, red is mostly high for the yellow cats, and it's mostly low for the green cats. So it might look pretty good as maybe the first question we should ask about. The first feature we should ask about, I mean. Green, on the other hand, is kind of all mixed up. The green values are kind of the same on both sides, so maybe that's not that helpful. So for deciding about whether or not a feature will divide the things up the way we want, one thing we can do is to put the cats on a number line according to their feature values. So here are all of the cats. See, that's clearly a cat. That's what that is. This is another cat. And I put them on a number line according to their value of nap red. So these are the green cats over here, and these are the yellow cats, plus this stray cat down there. And you can see that if I'm going to ask a simple question about nap red, like I'm going to divide this number line up somewhere, I could do actually a pretty good job. If I cut it like here, about 0.33 say, then everything on the right, everything that's greater is a yellow cat, and most of the things that are less than are a green cat. So that would be a good place to start. On the other hand, if I look at the green values, it turns out things are all kind of mixed up. So yeah, if I put a dividing line at, say, 0.5 and said that everything that's greater than 0.5 should be green, everything that's greater than 0.5 is green, so that's good. But on the left side, everything's all kind of mixed up. We almost have equal numbers of green and yellow. So this is not as good a feature to ask a question about. Okay. So step one is to identify the feature, and then we'll find a good place to split it in two. So when we're building our decision tree, we're going to start by asking a question about nap red. We'll ask if it's less than 0.33, and we'll check on both sides. One side will be false, and one side will be true. And step two is to look at all the cats that go this way, and look at all the cats that go this way, and decide what their label should be. Well, decide what their label should be if we can determine their label. Otherwise, decide what's the next question we should ask. So if we look at the cats that go down the left side of the tree, that would be all of the cats for which red is less than 0.33 is false. That's everything greater than 0.33, so all of these cats. They're all yellow. So I can immediately make this a leaf, and I put my label in, and I've got all the yellow cats. Done. For the cats that go down the true side, I've got mostly green, which is good. But I've also got this yellow, so I might not want to put a leaf here and say that they're all green cats, because that's not true. So I might ask another question. So when we think about all of the cats that go right down the tree, we're going to notice that they weren't all the same. And we're going to repeat step one. It's like we have a smaller database of cats. That's all the cats that went to the right. And we want a selective feature that divides them up well. That's exactly the same as step one. Okay? Just on this smaller collection. This idea of reusing a step on a smaller problem is called recursion. It happens all the time in computer science. And decision trees are usually built using recursion in this way. So if I looked at my cats that went this way, I might notice, for example, that I could divide them with green, which is not obvious, but suppose. And then once I've asked another question, again, I look at the cats that go left, I look at the cats that go right, and I see if I can label the leaves. And in this case, I can, and I'm finished. Okay. So decision trees are built automatically by computers in this sort of top-down way. You first find the feature that does the best job of dividing things up. You ask a question about that. Then you look at which way different data items go down the tree, and you ask questions about those subsets, and you ask again, and you ask again, and you ask again, until you get to the state where you know exactly what everything is. All right? Which is great because I don't want to have to do this manually. I want a computer to do it for me. I just want to get the images from Google and say, well, these are one class, and these are the other class, and just go build the tree. And that's what's done in practice. So there are a couple of odds and ends about decision trees. This process of taking labeled data, like data that have the features and then they have the labels with them, one class or the other class, the process of building a tree from those is called learning or training. I just want to mention a few keywords if you are interested further. The ways of telling how good a feature is, there are a couple of ways that can be done automatically. We did it by hand. There are two things called Gini index and information gain that measure inequality. And those are things that a computer can use. They're just arithmetic things that the computer can compute to decide which feature it likes the best. And there are lots of other tricks that people use when they're actually building these things. But the basic idea, you get it now. You've seen it. That's really all there is to it. The final thing that is important to note is that the more data you use, the better off you are. Because the more data you use to learn something, the more likely it is that when you see something you haven't seen before, you'll get it right. And it's basically a question of if you've seen lots and lots of data and you know what its labels are, then when you see something new, hopefully it's kind of similar to something you've seen before, and so it gets classified in the same way. Right? But having lots and lots of data, like millions of examples, can be really, really important. That's why we want to build these trees in an algorithmic way instead of by hand. So Now I'm going to show you how you could actually use one of these things. This is a little app that I wrote that is not taking pictures or putting anything on the internet. It is taking frames from the camera, and it is computing the nap for that frame. Here's how much red, here's how much green, here's how much blue. Okay? This is the nap for the picture of these lovely people here, plus the rest of the room. I also have little buttons that tell my computer whether or not I want a particular image to be considered positive or negative. No value judgment here, just two names for the classes. So if I want it to classify red as positive, then I show it something red. Notice that the red value goes way up, eh? The other values go down. And I'm going to say, OK, this is a positive example. Red's positive because our computer science color is red. So I'll give it some positive examples. And blue is going to be negative. Nothing against blue, it's just a name. So here's my blue. And you can see that the blue value goes up. The red and green, well, this is maybe more like cyan a little bit. It's got quite a bit of green in it, too. That's all right, doesn't matter. So my blue is going to be negative. I'm going to give it some negative examples. And now that it's seen at least one example of both classes, it's going to make a judgment call about whether it's looking at class minus or class plus. This is minus. Apparently, those people are minus 2. No offense. And if I show it my red, oh, plus, right, OK. So I have built a tree on these data down here. You guys, I know it's kind of small, but so each one of these is a nap. These are the class labels down here, some class 1 and some class 0. It's class 1 and then class 0. And my little app has built a decision tree that can distinguish at least this red from this blue folder. So I need 3 volunteers who've got something red and 3 volunteers who've got something blue. OK, so blue is our negative class. Yeah, right. OK. Let's try Crimson Tide. Unconvincing. Closer. So the thing about it is, closer. There we go. So notice that, OK, so because I'm taking an average over all the pixels in the scene, if it's really only going to call something red if it's really red almost everywhere. But they like that red, so that's cool. Next red, please. Closer. There we go. OK, so it liked that red as well. Great. Let's try a couple of blues. Blues. Back, front, doesn't matter. Blue. Blue. OK, so that's correct for blue. Let's try this blue. It's a little bit different. I'm not sure about this. Blue. Yeah, OK. So that's good. Let's try another red. Maybe the sleeve is good. Yeah, that's good because it's brighter. OK. Positive. Good. Another red. 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 Come on. There we go. Oh, OK. So good. This actually worked pretty well. Another blue. Oh, yeah. Sorry. Blue. Yep, that's pretty decisive. Last red. Oh, we have one more blue, too. All right. Well, that was good. See, and it's so even though this image has got a lot of gray in it as well, apparently there's enough red to set the thing off. It's because I guess we gave it enough examples that were a little bit different. The last blue one. Yep, it's deciding that that's negative. So that's great. Thank you, guys. That worked way better than I was expecting, actually. So in the other lecture this morning, I had somebody come down and was like, oh, let me show you my red thing. And it was actually kind of a burgundy color, and it did not like it. And so what we ended up doing was having to add examples to tell the tree that, well, this is also red or this is also blue. I wonder how pink, oh, pink is positive as well. No, it just, I hate when things work right. That's really, yellow is apparently class positive. So if I didn't like the fact that yellow was positive, I can give it some negative examples of something that's yellow, right? And now blue, I hope, is still negative. Yeah. Yellow is still negative. That's good. And red is still positive. Okay. And again, like if I wanted to see so green, it turns out that it's negative, but if I wanted that classified positively like red, I can give it some positive examples of green. And now we've got green is positive, red is positive, yellow is negative, blue is positive. Uh-oh, right? So it forgot. So we'll give it some more negative examples. So this is the trick. Negative, that was right. There we go, that was good. So the data that you give your computer, that's what really, really matters for these kinds of things. If you don't give it a data that's representative of the things you're going to ask it about, it is not going to succeed. Okay? Although in this case, it turned out to succeed pretty well, so that was cool. So take-home messages are, to a computer, everything is a number. Absolutely everything. Okay? But you can represent all kinds of stuff with numbers. You can represent all kinds of interesting, wonderful things like images and sounds and tweets and Facebook posts and whatever. Okay? And rather than tell the computer how to make a decision, you can teach it how to make a decision by giving it examples. And if that is the only thing you remember that you take away from this, I am totally happy. Because that is why I work here, and is what I love to do. So go out, try some of this stuff on your own. I'm actually going to try and post some of this code online in case, I don't know if anybody is teaching Python in school or you want to check it out after, but I'm going to post some of these resources so you can try it for yourself. But thank you very much. I really appreciate it.